All right, we are live. Officially. Welcome to Office Hours Round 4. All right, what's up? All right, let's get some questions up in here when you have them. I'm ready to take them. Yeah, totally. Until you do, and in the meantime, I'm going to keep plinking away on. Excuse me. I have a thing going with the. Oh, there we go. Okay, awesome. Anything about Lab 4? All right. Let's see. Probably. Excuse me, opening Lab 4 might be a good place to start. Alright, there we go. We are back. Okay, let's see. Okay. All of these are excellent questions. Or both of these. Okay, hang on. Sorry. For some weird reason, my keyboard isn't typing. Okay, okay, hold on one second. Okay. I see everybody asking questions, but I don't know why. My keyboard's not working, so I'm going to do a quick restart. Okay. But I'm pulling up the live chat on my phone while it does. Whoa! Let's mute me. There we go. Okay. Okay, so let's... Sorry for the technical difficulties. So, Susan, to answer your question, so for... Nope. Let's open that up. So when you are calculating the atomic mass, here's where, and it's, Susan, it's really good that you're practicing this because this will definitely be on exam 1. here are the things with significant figures that you should be aware of. So the mass of each isotope is measured, so you should take that into consideration. And then the second thing that you have to watch out for is the percent abundance is also a measured quantity. So so those are the two things that you have to watch for when it comes to sig figs. Okay. All right, that's going, which is good. Sorry, I'm just getting my live feed back up. Okay. Apologize to everybody who just blipped out. Okay, yes. So, okay, Jen, you were wondering about Susan's question. Okay, right. So the sig figs wise, you got to watch for the mass of each isotope and the percent abundance. You got to keep track of sig figs. Now, in the equation for the weighted average, right, there's that 100 in the denominator, right? So the weighted average is the mass of your first thing times its percent over 100 plus the mass of the second thing times the percent over 100 plus ... the mass of the nth thing, right? However many things you have over 100. Now here's the deal. These 100s in the denominator are exact. They're exact because they're based off the definition of a percentage. A percentage, to convert a percentage to a decimal, you divide by 100. So since they're not measured, you don't take them into consideration when you're calculating your sig figs. So that is how you handle sig figs for mass percents. You take into account the mass of each isotope, you take into account the percent abundance, but you do not worry about those 100s in the bottom. These have no sig figs. All right, hopefully that clears that situation up. Let's see, I posted a video in the discussions that help with the first part. Calculations pre-lab. Awesome. Brianna, thank you for doing that. Kate, let's see, when doing the orbital diagrams, how do you know how many lines to do with each block? Okay, Kate, great question. So for orbital diagrams, whenever you're doing orbital diagrams, and you're wondering, like, okay, we got the S block, the P block, the D block, the F block. We don't have to worry about the F block for this class. But you're wondering how many go with each thing. And here's how you do it. In the S block, there's only one orbital. No matter which shell it's on. It could be 1s, 2s, 3s. There's always one. For the P block, there are 3. And for the D block, there are 5. Just out of completeness, for the F block, there are 7. As you move from subshell to subshell, it's always +2. So the P has 2 more than the S. The D has 2 more than the P. And the F block has 2 more than the D block. So the way I remember it is S, you start at 1, right? Because we always start counting at 1. And then with each subsequent shell, the P subshell and the D subshell, there's 2 more. So the D subshell has 5 orbitals, the P subshell has 3, and the S subshell has 1. All right. Totally. Okay, so it looks like there's a lot of questions about Lab 4, but I don't know what they are. So my question would be what are your Lab 4 questions? Okay, awesome. Kate, I'm glad that helps out. So yes, I've got Lab 4 open and ready, but I do not know what your Lab 4 questions are. Oh, let's see. Okay, let's see. So there's a question on pre-calc for Lab 4. Let's see. Oh, so like how show your calculation for the theoretical percent of water for each of the following compounds. For each calculation, divide the mass by the amount of water. Okay. Oh, right. Okay. All right. Let's get into this, because this is actually it's actually ahead of where we are in lecture, but that's also why we're doing office hours during the lab time, so you can get the help that you need for the labs as you encounter them. I just need to make a note. To myself. Okay. All right. So here's what I'll do is I will tackle the first one, and then based on that, you guys will be able to move through and handle the rest. The first is so this lab is about hydrates, all right? And hydrates, that's a little, that pen's thicker than I normally use. So this lab is about hydrates. All right? And hydrates are literally, they are ionic compounds with water molecules stuck. Stuck to them. All right, these are compounds that water is very strongly attracted to. And so when you expose them to air, they'll literally suck water out of the air. Water gets attached to them, stuck to them. And so that's what a hydrate is. So, for example, and the word for this type of attraction is... we say that these compounds are agroscopic. Agroscopic means that that the compound will absorb water from its surroundings because water is strongly attracted to the compound. All right. So, so with the so that is that's hydrates are compounds that are agroscopic. They absorb water from their surroundings because water is very attracted to them. And now, so a couple more vocabulary words. So if you take, for example, calcium chloride forms a hydrate, a hydrate, and the way that is shown is this big dot is put there, and you go dot up to H2O. All right, that means that there is a 2, and it's not written here, but there's an implicit 2-to-1 ratio. There's 2 water molecules stuck to 1 molecule of calcium chloride, and so this is the hydrate right here. But it's also possible for you to have calcium chloride that does not have any water attached, and if you have just calcium chloride that isn't the hydrate, this is called, we say that this compound is anhydrous. So anhydrous means no water, and the hydrate means it has the water molecules attached. Now, as you can see by looking at this cover sheet, there's a bunch of different different numbers of water molecules, like copper to sulfate, for example, has 5 waters stuck to it. Cobalt to chloride has 6. Calcium chloride has 2. Calcium sulfate has 2. Magnesium sulfate has 7. All right. So there's no predictable pattern for how many water molecules will attach to the ionic compound when you form the hydrate. You just have to you have to be told, and we will tell you. So you are not expected to know how many water molecules will be in the hydrate. All right, now that we know what the hydrate is, we know what anhydrous is, we know what agroscopic is, we can do some of these calculations. So they want us to calculate the theoretical percent of water. All right, and here we're talking about a mass percent. Oops. The mass percent of H2O, all right? And to find the mass percent of H2O, I don't know why I wrote it up there, because I got a longer equation I need to write. To find the mass percent of H2O, it's equal to okay. And I totally, just to let everyone know, I totally see that there are more comments piling up. I'm just gonna finish this and then I'll hit you in order of the asking. So the mass percent of water is going to be equal to the mass of water divided by the mass of the hydrate. All right, so you find the total mass of the hydrate, the mass of water in the hydrate, divide one by the other, multiply by 100. That'll give you your mass percent. So let's do this example for just for the first one, for cobalt chloride. All right, so we're going to do it for cobalt chloride hexahydrate. We're going to start by looking at our mass of water. To calculate the mass of water, we need to look at the periodic table. All right, so hydrogen has an atomic mass of 1.008 AMU. Oxygen has an atomic mass of 16.00 AMU. And the thing about hydrogen is we have two hydrogens in one water molecule, so we need to multiply this by 2. All right, so this will give us 2.016 AMU plus 16.00 AMU. Oops. You add these together and you get 18.02 after rounding, right? Oh, here, let me just write this out. 18.16 AMU, but now we got to look at sig figs. We go with the least precise, which is in the second decimal place. So the mass of one water molecule is 18.02 AMU. Now here's a question. All right, that's the mass of, right here, one water molecule. How many water molecules do we have in this hydrate? And the answer is 6. So the mass of water really is going to equal 6 times 18.02. All right, so the mass of water that we're going to use here, that's not my calculator, 6 times 18.02 is 108.12 MU. And this 6 is not measured, it's exact. So we're going to keep 4 sig figs. So 108.1 AMU, excuse me, is what we're going to keep. All right, this will be our mass of water that we use for this calculation. Now, we know the mass of water. So we've got that numerator taken care of. We need to figure out the mass of our hydrate. So the mass of our hydrate is going to be cobalt plus our 2 chlorides plus our 6 water molecules. It's the whole tamale. And we actually already know what the mass of our 6 water molecules is equal to. It's 108.1 AMU. Chloride, when you look it up, is 35.45. AMU, and we got to multiply this by 2, right? And then cobalt, I don't actually know off the top of my head. This is what periodic tables are for. Cobalt's going to be larger than the elements we've been looking at so far. Yeah, cobalt is 58.933. All right, so after we multiply 35.45, right, this is going to be 70.90. We've got 98.933, and we have 108.1. So let's add these together. This gives us the mass of our hydrate is 277.933. Our last sig fig can only be in the first decimal place, so after rounding, 277.9. All right, this is the mass of our hydrate. And now we're ready to calculate our percent mass of water for cobalt 2 chloride hexahydrate. So the mass of the water, 108.1 AMU, over the mass of our hydrate, 277.9 AMU, times 100. You'll notice that our mass units cancel, which is good because we're calculating a percentage. Percent doesn't have units. 108.1 divided by 277.9 times 100. Oops. So I'm getting the value that I'm getting is 38.89888. However, we can only keep 1, 2, 3, 4 sig figs. 8 rounds that 9 up to a 10, which subsequently rounds that. Oops. Ooh, there we go. That 8 up to a 9. But we still need 4 sig figs, so I have to add a 0. 38.90%. Oh, did I mess things up? Let me see. Okay, let's see. I don't. Let me, Prathana, let me check. Unless my math is wrong on the other pages, it's 38. But let's just take a look real quick. Okay. And actually, let me pull something up. Okay, let's see. I'm just double checking my math real quick. And let me make sure I pulled the right atomic mass for cobalt. Yeah. Alright, so oh, snap. Okay, I did make a mistake. It was my math. Oh, snap. Okay, hang on. There we go. I messed up right here. The mass of cobalt isn't... No. The mass of cobalt is not 98. It is 58, which would make the total mass not 277, but 237. So let's change that again. And then that has dramatic effects over here. Nope. If this is 237, then I'm just going to get a completely different number over here. Still with 4 sig figs, though. Okay, let's crunch this one more time. 108.1 divided by 237.9 times 100. So the correct value, excuse me, is, let me just double check that, 108.1, 237.9 is 4, or here, I'm going to do this in blue. $45.43926, rounding to 4 sig figs is 45.44%. All right, so that is the total. Oh, okay. Right, okay, hang on. Okay, so Corinza, here's the thing. The mass of yeah, the whole thing. So it's the cobalt plus the chlorine plus all the waters. The water's part of that total mass. Okay, Susan, there are 2 sig figs in the decimal for the final answer, but only because notice that we use 4 sig figs in our numerator and 4 sig figs in our denominator, so our answer must have 4 sig figs, when you're multiplying, you don't look at the number of decimal places. You only look at the total. And so since we have 4 and 4, the answer must have 4. So it doesn't matter how many decimal places you have. You just have to end with 4 sig figs. Okay, yes, 45.44, totally solid. That's what I got to. Let's see. Okay. So yeah, 45.46. Brianna, your answer is spot on. Again, there may be small fluctuations in the decimals due to rounding, but that number is correct. Okay, wait, after what? Okay. Okay, right. So here's the thing to remember. When we are talking about multiplying and dividing. All right, so for multiplication and division, you count the total number of sig figs. All right, you look at the total number, whichever one has fewer, that determines the amount of sig figs. It's when you add and subtract that's when you look at the precision. Which is often the decimals. With order of operations, it's a little confusing. Should we do... Okay, so maybe doing another example, like doing... here, I can pull off another one of the... I'll do... I can do calcium chloride, for example. And then we'll work through this again, and maybe we'll reach some enlightenment. Okay, so instead of cobalt chloride, let's look at calcium chloride. All right. Brianna, I can totally go over homework 2. Problem 9. Maybe after I do this one more percent of a hydrate, and then I'm just like queuing it up. Yes, yeah, totally. I can totally hit that. Hit that up. Okay, so again, our percent mass of H2O will be the mass of water divided by the mass of the hydrate. This is, for this molecule, going to be 1 calcium plus 2 chlorines plus 2 waters. All right, so the hydrate is the whole thing. The mass is just the water. So first, we need to find our mass of H2O. And I know we literally just did this, But I'm going to take it one step at a time as if we hadn't and apply the rules for sig figs as we go. All right, so our mass of water, we have per hour thon. I can totally hit question 11 in homework 2 as well. So hydrogen has a mass of 1.008. Oxygen has a mass of 16.00. The mass of water is going to be the mass of hydrogen plus the mass of hydrogen plus the mass of water, right? Because there's two hydrogens. So it's going to be 1.008 AMU plus 1.008 AMU plus 16.00 AMU. When you add these all together, they add to 18.16 AMU, but when you look at your sig figs, the significant digit, last significant digit in hydrogen is in the third decimal place, but the last significant digit in water is in the second decimal place, so our answer must be rounded to the second decimal place. Totally homework 6, we can hit it up. So the mass of one water molecule will be 18.02. All right, AMU. Now we don't want to know the mass of just one water molecule, right? For us, we have two water molecules in play, so we need to know what the mass of 18.02 AMU plus another one, right? We have two of them. When you add these together, they sum to 36.04. And the last sig fig in both of those numbers was in the second decimal place. And so the answer must have its last significant digit in the second decimal place. 36.04 does. So this answer is good for sig figs as is. No need to round. 36.04. Okay. That's our mass of water. Let's find the mass of our hydrate. Now remember, the hydrate is the entire molecule. All right, the hydrate is the entire molecule. That means we're dealing with the mass of calcium. Oops. Plus the mass of chlorine, plus the mass of the second chlorine, plus the mass of two water molecules, right? The mass of calcium. Oh my gosh. Brianna, it would, you would not be alone. I'm pretty sure the entire class would show up for that throwdown and just like kick sig figs to the ground and just start like beating them. No mercy, because sig fig shows no mercy to you. Let's pull up these atomic masses. Calcium is 40.078. Chlorine is 35.45. Chlorine is also 35.45. And we just calculated the mass of the hydrate. Two water molecules have a mass of 36.04. .078. All right, so our sum here These all add to 147.018. But sig figs wise, chlorine and our mass of all our water molecules have their last significant digit in the second decimal place. So that is what we round to. So 147.02 AMU is the mass of our hydrate. All right? Now, we know the mass of our hydrate, we know the mass of water, we can calculate our percent mass of water by dividing the mass of our hydrate, 36.04 AMU. Oh, Peyton. Oh, I just noticed your YouTube profile pic is your pups. We are doing right now. This is a Lab 4 pre-lab calc. Number 3. We did number 1 already. I made a mistake the first time through, and then I went back and corrected it. I have not made a mistake yet, to my knowledge, on this one. But this is Lab 4 stuff. So we take those two, divide the mass of our water by the mass of the entire hydrate, and there we go. Divide one by the other, multiplied by 100. And the value that my calculator is telling me is 24.51400,509. However, our sig figs are limited by our numerator. We have 4 sig figs in the numerator. There's 5, you'll notice. 1, 2, 3, 4, 5 in the denominator. But when you're dividing, you got to go with whichever has fewer sig figs. So we roll with 4. 1, 2, 3, 4. The 4 after the 1 will round down, and so our answer, correct value with the correct sig figs, will be 24.51%. Cool? So there's one without a mistake. I was also a little more methodical on the significant figures for the calculation. Hopefully everyone was able to follow. Please let me know if it doesn't make sense. We can definitely dig into it. We are only 48 minutes into our 3-hour office hour, so we have the time. Yes, dude, the FOMO is real. Totally. Okay. So there are, if there are no further questions about this, there's a slew of questions about the homework set, which actually I'm going to write them down. So we don't miss them. There's number 9, number 11, number 6. Okay, awesome. Okay, so let's take a look at some of the homework stuff. I have to liberate my ears because I have been wearing those headphones for a long time, and it's great audio fidelity, but they are not comfortable. All right, let's take a look at number 9. Okay. Actually, I want to see this here. On the verge of tears. Whoa. Yes, Yeah, totally, Jen. We're moving on to some homework. It's going to be nice and chill relative to what we just did. And then we can, you can circle back at your leisure. Which, again, Lab 4... So if you're feeling overwhelmed, remember, Lab 4 and Quiz 4 aren't due till the 25th. So a week from today. So you have some time to work on that material. And not including this office hours, you've got 2 office hours in between now and then. So you've got some time to go over this, to study this, to absorb it. So, treat yourself kindly, cut yourself some slack. Okay. Let's open up a new slide. All right. Okay, so homework 2, question 9. Now I'm not going to do do the exact same problem, mostly because oh, you know what? Screw it. You guys are you're the ones who are here in office hours, right? The most committed of the class. I'll totally do this one, the exact one with the numbers. So because that's the one you guys have all been going over and you're wondering, is my answer right? Let's just do this thing together. Okay, so 2 naturally occurring isotopes exist for the hypothetical element dipium. Sorry. Dipium sounds like a silly name. 25% of dipium has a relative mass of 17. Okay, this is where we're getting real. 17.02 AMU. And the other isotope has an abundance of 21.03 AMU. Okay, so let's... All right. So these are 2 masses, right? Now let's look at the percents. So the one with the mass of 17... Oh, cancel that. Has a mass of 25.0%. So we throw that over 100. We're going to do the same thing to 21.03, except it's 75.00%. So we throw that over 100. I'm actually going to separate these out a little bit. Give them a little room to breathe. All right. I want to scoot this down just a hair. Okay, so let's look at this because we have an interesting sig fig situation. All right, that's me grabbing my my phone / calculator. Oh, you know what, Susan? I'm so glad you pointed that out. Mine does as well. 17.0. There we go. Okay, so let's do this. Oh my gosh, is that my second? I am tripping so hard. Yeah, it's 21.30. Holy moly, Jen. Thank you so much. That would have a drastic impact on our answer. and confuse everyone in the end. At this point, you guys deserve the you deserve the actual answer because you're better at doing math than I am. Yes, thank you guys so much. So much. Okay, so let's do this now with our first one. All right, now that we got the right number, 17.0 times 25.0 divided by 100. My calculator is giving me a value of 4.25 units AMU. Yeah, you guys are scoring huge brownie points. Gold stars all around. All right, now let's look at our sig figs. All right, 17.0 has 3 sig figs. 25.0 has 3 sig figs. So our answer must have 3 sig figs, and it does. So we do not need to round, we don't need to add zeros, it's good to go. Let's do our second calculation. 21.3 times 75 divided by 100. This value is 15.975. All right, that's our value. Let's look at our sig figs. 21.30 has 4. 75.00 also has 4. So we can keep 4 sig figs. Once we round, this will be 15.97. Oh, sorry. 98 AMU because 5 rounds up. All right. Now for the last step in this calculation, we take 4.25 AMU and add 15.98 AMU. 4.25. The value that I get is 20.23, but let's look at our sig figs. We just added, right? We just added. So we have to look at the last significant figure in each number. For both of these, the last sig fig is in the second decimal place. So our answer must have its last significant digit in the second decimal place, and it does. So there's no reason to round. 20.23 AMU is the correct value with the correct sig figs and the correct units. And I just checked to make sure that that's what I have it marked as on the quiz, and it is. So 20.23 is the answer to number 9. Okay, prior thought, how many labs are we getting till next week? So I'm not quite sure I understand the question, but what I can tell you is in the syllabus it'll tell you when everything is due. So yeah, well done. So quiz 3, what's today, the 18th? Quiz 3 and exercise 3 are due tonight at 11:59. Quiz 4 and exercise 4 is the only one that's due next week. Then the following week has two things due. Quiz 5 and exercise 5, quiz 6, exercise 6. Right now, only lab 5 is available. Lab 6 is not yet available. Dude, that's awesome. It's awesome. It's the best feeling in the world when something makes sense. I think, at least. Okay. Okay. So that... Susan. Okay, thank you. Excellent. So the percent abundances are always measured. The percent abundances are always measured. They're not exact. So these guys up here are measured. Both of those are measured. What's exact are these. Whoa, what the heck was that? The denominators are exact. But those numerators are measured. Ah, Susan, great question. 25% has 2 sig figs, but 25.0% has 3 sig figs, and 75.00% has 4 sig figs. They're not all the same. Adding decimal places in chemistry changes your number of sig figs, and so even though the value is the same, the precision is different, and it will influence your answer, as it did in this problem. Okay, so Susan, so here's the thing to remember. So here's the thing to remember about zeros and sig figs. All right, this is everything you need to know about zeros and sig figs. Zeros are significant under 2 conditions, all right? Yes, totally. But here's the reason. If zeros are between sig figs, they're significant, and they're significant if they're both at the end of a number and to the right of the decimal. All right, so the reason why 3.000 has 4 sig figs is because we have a non-zero, and then we have a 0 that's to the right of the decimal and at the end of the number, and then 2 zeros that are in between significant digits. That's why 75.00% we have 2 non-zeros 1 0 to the right of the decimal and at the end of the number, and 1 0 in between. So this has 4 sig figs. So, all right. Let's see. Okay, so they actually have several questions about homework. That was number 9. Let's go ahead and move to 11. All right. Okay, so let's Let's take a look at this one. All right, number 11. Which of the following statements is consistent with the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. All right. So we're looking for a consistent statement, and we have a few of them. Oops. So let's see. A. And these will be in a different order than yours are because they're shuffled every time, but you'll have all of the same selections, just in a different order. So A, there are 2 electrons. 2 electrons in the second shell. Let's see. Oh, gotcha. Gotcha. Okay, good, Susan. I'm glad that helped. Yes, totally. Carolyn, okay, you don't mind skipping the calculations. You know what's funny is I might not mind skipping having to make a data sheet of problems. But we'll see if I have enough time. Okay, so that's option A. Option B. There are 6 electrons present in a 3p orbital. Let's see. Okay, totally. Dude, this is where the rubber meets the road. The most important study habit for any chem class is doing problems. It's exactly for moments like this. It's like you have it down right in your notes, but then you go to do it and you realize like it's not everything is totally in there. This is where learning actually happens. It's not in lecture. It's not in note taking. It's in problem solving. Okay. Dude, lab 4 is a good lab. It's a really good lab. It's a hard lab, but it's a good lab. It looks like I got to cook up a data set for that situation. Or do I? You know, hold the phone. I'm going to see. I'm going to check something out real quick. Nice! Dudes, guess what? There's totally a data set already made. I'm going to share this. I'm going to share this for all of you guys to use. Oh, this is the entire thing with answers. I'm going to make a modified version that doesn't have answers in it. And I'll share it with you. Okay, so... okay, so I'm gonna share this business. I know. It's really important though. It's difficult. But so is science, right? It's a really good lab. And I'd be doing you all a disservice if I just didn't give it to you. So I'll be posting an amendment to no, you guys just want the Excel spreadsheet that I'm looking at right now. We'll see. Okay, let's. I keep getting sidetracked from problem 11. There's A, B, C. C says, ooh, let's get back to black. There are an equal. Yep, exactly. Carenza, that's exactly it. As you can ask for help, I can help you through it. It'll all be good. They're equal number of electrons. Dude, yeah, you guys should like make a Chem 305 Discord or something like that. That would be super, super awesome. Let's see, equal number of electrons present. In each subshell. Oh my gosh, Jen, that just killed me. That was so good. A, B, C, D. Until the next phrase. Yeah, the lab from hell until. Yeah. It's so good. I love it so much. It's a real challenge. D says there are more electrons present in the second shell than the third shell. And then E, final option. There are 6 electrons present in a 3p subshell. All right. Okay, and again, just because I read this problem like forever ago, and now we're just getting back to doing it. So this problem says, which of the following statements is consistent with this electron configuration? And again, this is homework 2. Let's do that just better. Homework 2. That looks even uglier. Homework 2. Question 11. All right. So what we have to do is we have to go through and process of eliminate, find which ones are incorrect, identify which is true. If you look at letter A, 2 electrons in the second shell. All right, the second shell is everything on the second energy level, right? This is clearly incorrect because there are 8 electrons on the second shell. Okay, so A can't be an option because there are 8 electrons on the second shell. B, there are 6 electrons present in a 3p orbital. This one can't be right because there are 2 electrons max in any given orbital. So B is incorrect. C, equal number of electrons present in each subshell. This is straight up wrong because the first subshell only has 2, the second one has 8. So that cannot be correct. D, there are more electrons present in the second subshell. There I go being Sean Connery. Subshell than the third. Well, we've seen that there are 8 electrons in the second. But if you look at the third shell, there are also 8. So there are not more electrons present. So D is wrong. So we know that E has to be correct, but let's look at why. E says that there are 6 electrons present in a 3p subshell. That is correct because there are 3 p orbitals in a p subshell, and 3 orbitals hold a maximum of 6 electrons, and that is exactly what we see here in this problem. So that is the answer to number 11. Again, it may not be E in yours, it jumbles up the answers every time, but that is the correct one. All right, let's look. There's another homework question. Number 6. Let's see. Chlorine, which exists in nature in 2... what is the difference between an orbital and a subshell? Carolyn, great question. Let me answer that before I dive into a new problem. So, for example, let's look at oxygen. I'm going to write it over here. With an electron configuration of helium as its noble gas abbreviation, 2s2, 2p4, right? And we could write out the orbital diagram like so: 2s, 2p, 2 electrons in the 2s subshell, and 1, 2, 3, 4 electrons in the 2p subshell. Now, the way to think about an orbital is an orbital essentially is a room that can hold 2 electrons. So for example, this guy right here is one orbital with 2 electrons. This guy right here, I should say one, not just one orbital. This is one p orbital with 2 electrons. This is one p orbital with 1 electron. All right, so an orbital is just a 2-electron house. It's a blob that can fit 2 electrons inside of it. A subshell is a group of orbitals of the same type on the same energy level. All right, so a subshell is a group of orbitals of the same type on the same energy level. And so we could say that there are 2 subshells present. All these orbitals together, oops, let me switch to my, here we go. All of these orbitals together comprise the 2p subshell, because it's all the p orbitals on the second energy level, whereas this one single s orbital is the 2s subshell, because there's only one s orbital on the second energy level. Yes, yep, Carolyn, that's exactly it. Like a subshell is like a container for orbitals. Electrons are in the orbitals, 2 per, and then the orbitals are in the subshells. And then the shells hold all the subshells. It's like Russian dolls here. All right. Okay, let's see. So that's the answer to the difference between orbitals and subshells. Parthana, we can totally get to question 8. But before we were going to do question 6, I think Jen asked for question 6. Ah, yes. Susan, I can actually, before we leave this idea. So, so an orbital, we're going to do holds 2 electrons. A subshell holds orbitals of the same type. And a shell holds the subshells that have the same energy. Right, first energy, second energy, third energy. And then the atom holds the shells. All right, so you've got orbitals being held by subshells, subshells being held by shells, and then shells being held by atoms. That's kind of the descending order. Yeah, Jen, you got it. Totally. Shells are bigger than subshells, which are bigger than orbitals. And that's how you get from atom to electron. It's the Russian doll of atomic structure. Okay. All right, Jen, you have been crazy patient. I don't even know how long ago you asked for homework 2, question 6. But we're here now. We made it. All right, let's take a look. Chlorine exists in nature in 2 isotopic forms. Oh, and it has a mass. Okay. Realistically, I might be able to get to it today. If not today, I will be able to get to it tomorrow. One of those two. It's on my to-do list, but like my urgent to-do list. So within 24 hours, it'll be going up. Okay, yes, totally. Okay. What was I doing? Oh yeah, homework 2, question 6. So chlorine exists in nature in 2 isotopic forms, and it has an atomic mass of 35.5 AMU. So here, let's just write this out. All right, so with this one, we're told there's 2 isotopes, and yes, yeah, I totally will. Okay. 2 isotopes, atomic mass of 35.5 AMU. And so so we have to, they're asking us to that means, and then they give us a not a bunch of answers. They give us 4. That means that, oops, 35.5 AMU is the upper limit. For the mass of a chlorine atom B more than half more than half of all chlorine atoms have masses of 35.5 AMU. C, the mass of one isotope is larger. Oh, sorry, it says lighter. And the other is heavier than 35.5. And then D means that all chlorine atoms have a mass of 35.5. All right. Okay. So let's do this. Oh, hang on. Okay. Okay, so we have to figure out which of these is correct. One of these is correct, and 3 of them are incorrect. Now, the thing to remember is, so we're told that chlorine has 2 isotopes. All right. Chlorine has 2 isotopes, and that its atomic mass, which is a weighted average, is 35.5. So if it's a weighted average, that means that we know an average always falls somewhere in the middle of a range of values. So we know that A is incorrect right out of the gate. Because even a weighted average will never be equal to the max. So it's not an upper limit. B, more than half all chlorine atoms have masses of 35.5. If half of them had masses of 35.5, then when you took the average would be lower, so that is also incorrect. The mass of one isotope is lighter, the mass of the other one is heavier. this one is actually true, right? Because if 35.5 is a weighted average, right, if it falls in between the two masses, one's got to be heavier, one's got to be lighter. D, all chlorine atoms have a mass of 35.5. This one is false because we know that there are two isotopes. If they all had the same mass, there would be one isotope. But we were told in the problem that there were two, so that is why D is wrong. So C is our correct answer. Hopefully that made sense. All right, Parthana, you were asking about question 8. And your question is there any answer which doesn't fit any of the category? I can't, those are beans that I can spill. I should qualify that. Sometimes there's a category that nothing goes in, but for this problem, there is one for each category. Totally. But we are a minute and 42. One minute and 42 seconds in. We're an hour and 42 minutes in. Okay, awesome. And possibly at our first lull. All right, so I'm still here. I'm still available. Okay, let's see. I think I understand this question, but I just wanted to make sure. Can we get some help on homework 7? Yes, we totally can. Totally can. Let's take a look. 7. Choose an appropriate pair that contains the same number of nucleons. Okay, so with... Oops. Nope. Let's do this. So homework 2, question 7. So here I ask you to choose a pair of atoms with the same number of nucleons. All right, and the key to this one is remembering that nucleons is a term that means protons and neutrons. All right, so essentially, if something has the same, if two atoms have the same number of nucleons, then they will have they'll have identical or the same mass numbers, right? Because the mass number is the total number of nucleons present in a nucleus. So really, you just look, and it doesn't matter what elements they are. You just look for two elements that have the same mass number, and you got it. All right, Susan, let's see. Example 2s2, 2p4. Shell is denoted by the first yup which is equal to the period, yes. So the total number of electrons in the second shell would be 6. Susan, that was a... Homework 7 isn't showing. Okay, yes. That was. I believe I have noted that. Yes, Susan. So, you had emailed me about a different homework problem where I had put an image into the rich text editor for the answers, and then it didn't show up for you guys. And 7 was the same mistake, but this was the same homework set, so I couldn't fix it. So everybody's automatically getting number 7 correct. So don't worry that you can't see number 7. I think there were a couple. It was number 7 and another one. But I'm automatically crediting 2. I'm gonna add 2 points to this homework set. So, because a lot of people couldn't see that one, and I think the other one was, let me see, where was it? It was number 7. I think number 8 as well. Totally. Okay, Kate, a little confused on lab 3. Okay, let me pull lab 3 up. Okay, on lab 3, how do we time how long a stick? Right, yeah. Yep. All right. Of course. Let's see, to find the total number of subatomic particles in the atom. You sure do. Yeah, well done. That one was a little tricky, but you cracked the code. Also, if you see me looking away, I'm going to start kind of like answering emails, but only in the apparent lack of questions or the question slowdown. If you guys have them, hit me with them, and I'm totally interruptible. Let me see. I don't know if you can hear that, but that is that's my 2-year-old. Oh man, he's on his last hour. Well, not hour, maybe he's like got an hour and a half to 2. But it's always when he gets the most energetic for some reason. I have no idea how that works, because that's when my wife and I are bottoming out, energy wise. Oh my god. Oh my gosh, that's so good. Dude, and you guys are all like doing it hardcore. Because it's summertime. Like, literally, we've been doing this 2 weeks. You guys have had to absorb a month's worth of material in that time. So, you know, you guys are full metal. You're hardcore Henry, as far as I'm concerned. Prathana, let's check this out. I don't know off the top of my head. Let's take a look. Awesome. Kate, I'm going to answer Prathana's, and then we will hit your question about Lab 3. So, CL37. Versus Argon 36. All right. CL37 has protons plus neutrons. It's 37. Argon, protons plus neutrons equals 36. Now for the number of electrons, we got to look it up on the periodic table. Argon has 18 electrons. Chlorine has 17 electrons. When we add 37 and 17, it adds to 54. And when we add 36 and 18, it adds to 54. So yes, same number of subatomic particles. Who's Henry? Oh! Carenza, it's not just Henry. It's hardcore Henry. Which was the first movie shot entirely from the first person. So like, you know, like in like video games where you can see like your hands and you've got like your guns, but you like just see your hands in front of you. The entire movie, Hardcore Henry, was shot with the like you just see his hands. It's like you're looking through his eyes. It was a trip. Yes. Okay, good. Parthana, you did awesome on that one. Okay, Kate, let's see. It's on the burning wood part. Okay, it's asking about demonstration of a property of oxygen gas, but I look through the properties, nothing explains it, unless I'm missing something. Okay, let me, yeah. It is a trip. I can't remember it. It used to be on maybe Netflix or Hulu. I don't remember which one had it, but one of them did. It came out maybe around 2010. Okay, so Kate, I'm looking up the burning wood part. Okay, burning wood, ignited wood, splints, observations, how long, obtain a bottle full of air, repeat step one. Question, the glowing splint test demonstrated what what property of oxygen. Okay, let's see. Let me go back. Okay, hang on.
You'll notice that
Whoa.
it reignites in just the house there. Okay, so what I do is I blow out the wooden splint to where I just have glowing embers, and I plunge it into the flask, and you want to note and see what happens. And you'll notice that it reignites.
It does multiple times. Okay, let's see. So I think, so Kate, after looking at this, Oh yeah. Totally, Kate. That's the only thing I could see. So totally, I'm glad it makes sense. Ah, Persona. Yeah. Okay, let's see. Doing the practice homework, if there's an element like tin, for example, and there's a number attached to it. Ah, okay. Carenza. So here, whenever you have, so this is the isotope nomenclature. You've got the elemental symbol, mass numbers up here, atomic numbers down here. So this guy up in the top, always mass number, and here down below, this one's atomic. So here we got all our nucleons. And down here we have our protons. Of course. Anytime. any chance, did you touch/review the carbon? No, I didn't actually. Would you like to do some because I totally haven't touched on that yet. And we still got like 40 minutes to party here. Ah, yes. Oh, okay, yes. Jen, excellent question. Let's get into it. So here's the thing. So let's name this compound. All right. Now, the name, as we know, is going to be cation plus anion. With an "ide" added on to the very end. All right. We know that's how we're going to name this thing. Cu, its name is copper something, copper blank, and then Cl is chloride. Copper blank chloride. All right. Now, what goes in here is the charge on copper. All right? The charge on copper goes in a parentheses in Roman numeral next to copper. All right? So what we need to do is we need to figure out what that charge is. All right? We need to figure out what that charge is. Now, to do that, we have to use what we know about ionic compounds. Because the thing is, we know that our total positive minus our total negative for the compound equals 0. All right? All of the positive charges plus all the negative charges add to 0. In this compound, we don't know the charge that copper has. But we know that we have 2 chlorides. And if we add that positive charge on copper and the negative charge on chlorine, it's going to add to 0. All right? Now, we don't know what copper's charge is, but we do know that chloride has a charge of -1. We know this from looking at the periodic table. So copper plus 2 times the charge on chloride equals 0. All right? This means that copper minus 2 equals 0. And so when you solve for the charge on copper, copper will have a charge of +2, and that's why we put a 2 in the parentheses. All right, that Roman numeral 2 means that copper's charge is +2. It's the charge on copper. It's not the number of copper atoms present, because there's only one copper atom but the charge that that ion has is a positive 2 charge. And the reason why it's a positive 2 charge is because that one copper is balanced by 2 chlorines. Each chloride has a negative 1 charge. So if we've got 2 negative ones, we need a positive 2 so that they balance each other, so that they cancel out. Does that make sense? Okay, let's do another. So okay, so let's do this. Jen, let me ask you some questions. So this is the crux of it. Let me know if you're tracking with this. Does it make sense when I say that every ionic compound is net neutral? And by net neutral, oops, net neutral means that the positive charges, okay, so you're tracking there. Okay, that's good. Yes, and it's more than it wants to be. With ionic compounds, I almost said anionic compounds. At Jen. Every ionic compound must be net neutral. All right, every ionic compound must be net neutral. So that governing principle will allow us to determine what the charge of our transition metal is. All right. So, for example, let's say I want you to name TiO2. All right. Now, Ti is a transition metal. Its name is titanium. Oops. Titanium. All right. And we don't know the charge, so we have to leave a parentheses blank. We need to figure out what goes in that parentheses. Now, O is oxide. All right, titanium oxide. But the thing is, we need to figure out the charge on titanium, because part of naming any transition metal is you must determine what charge it has. Right? So, I'm going to be a little bit more explicit when I write out the expression. We're going to use the fact that we know that this compound is net neutral to determine the charge on titanium. Jen, I have a question for you. Well, actually, before I ask it, I'm gonna write this out. All right. So here's the deal. Here's where the net neutral thing comes in. Net neutral means that the charge of titanium plus the charge of oxygen has to equal 0. And it's not just the charge of oxygen. It's 2. Oops. It's 2 times the charge of oxygen because we have 2 oxygen atoms in this molecule. Are you with me so far? This is what it means to be net neutral, that the charge on titanium plus the charge of both oxygens must add to 0. If not, it's totally fine. I'm just trying to find where it goes off the rails for you. Okay, we're good so far. Okay, awesome. Now, we don't know the charge on titanium. We don't know the charge on titanium. But we can get the charge of oxygen from the periodic table, all right? You'll look it up. Oxygen has 8 electrons. It wants to be like neon, its nearest noble gas. Neon has 10 electrons, so oxygen picks up a charge of -2. So the charge of titanium plus 2 times, now we know the charge on oxygen, is a -2 equals 0. That means the charge that titanium has, 2 times -2 is -4. Charge on titanium minus 4 equals 0. And now if we solve, if we add 4 to both sides of this equation, we get the charge on titanium is equal to +4. All right. How are you so far? Excuse me. Okay, now, this is awesome. This, oops, I want that in green. This number right here is the charge we're looking for. So once you know the charge of titanium, you put that in Roman numerals in parentheses. -2 comes from the periodic table. is the anionic. Alright, so once you determine that charge, you put it in parentheses in Roman numerals next to your transition metal, and that is the name of the compound. Oh yeah. Yes. Yeah. Do you want me to do one that moves in reverse? All right, let's hit it. Let's hit it. Oh, good. It's my favorite thing about office hours is it really is humans helping humans. Okay, so here's an example of this type of thing moving in reverse. All right, so let's all right, yeah, let's do this. Let's say so with this one we're going to write the chemical equation for Iridium 1 sulfates. We'll throw one of our polyatomic ions in. All right, now iridium, our cation, is a transition metal. Its abbreviation is IR, and transition metals are cool because this is the charge that your cation will have. So iridium here has a charge of +1. So Corinza, these are basically they're naming problems. Will either say name this compound or write the chemical formula. Oh, sorry, I said chemical equation up here. It should be chemical formula. So it'll either be name this compound or write the chemical formula for it. Alright, now sulfate is a polyatomic ion. Sulfate is SO4 and it has a charge of -2. And so then we have to ask how many cations balance our anion. Right? And we have a charge of +1 and a charge of -2, so it's going to take 2 positive cations to balance with our anion. So this will be, we're going to need 2 iridiums to pair with our 1 sulfate. So iridium 1 sulfate is IR2SO4. All right, and that is an example of the reverse direction. Yes. I think there's around 10 of them, polyatomic ions that you got to memorize, that I would recommend memorizing. But again, if you ever come across one that you're struggling with, just look it up real fast. But it'll definitely make your life faster to just have them memorized. I sure can. Oh, I don't know what Y1P means. I meant to say yep. Okay, so the maths here. Remember, we got to be net neutral. That means that our charge for iridium, Carenza, I totally can, plus the charge for sulfate needs to equal 0. All right, it must equal 0. The problem here is my charge for sulfate is -2, and my charge for iridium is +1. And Jen, you know that 1 minus 2 isn't 0, it's -1. That's why we need 2 iridiums, so we can multiply that charge by 1. That's why iridium that's why we have 2 iridium cations in our molecule. It's to make sure that we're net neutral overall. So that we do indeed add to 0. Does that make sense? Okay. The 4. Yeah. So you only look at your positive and negative charges. I think, yeah, let's maybe do another one. I think it'll help kind of get some reps in. Okay, so let's write the chemical formula for ... Let's do another one. Let's do tungsten chloride. Well, so here, let me actually hop back. So the charge is still there. It's just being canceled. So the charge on sulfate is still there, but because it's paired, that -2 is paired with two positive ones, we don't actually show it. We don't write the charges when they're paired together like this. Because the two iridiums are canceling, the two positive ones are canceling the -2, so you write it without any charge when you write them together. You only write the charges when you write them separate from each other individually. Does that make sense? So, like, for example, if you looked at NaCl, you would say the name of this compound is sodium chloride. And we know that sodium has a charge of +1, chloride has -1. Yes, okay, good. But together, when they're one unit, the charges cancel. I.e., balance each other. Okay. So, with all of that in mind, let's write the chemical formula for tungsten chloride. All right. Now, tungsten is a transition metal. Its symbol is W, and we know that it has a charge of +5 because this is our charge right here. Right? The charge is inside that parentheses. Chloride, we can determine chloride's charge from the periodic table. It wants to pick up one electron to be like its nearest noble gas, argon. So it picks up a charge of -1. So now we have to ask how many chlorides do we need to balance with our tungsten? And we need 5, right? Because we've got a positive 5. We need 5 negative 1s to balance. So together, this will be WCl5. Because it's 1 positive 5 with 5 negative 1s. Does that make sense? Nope. Okay. Ah, yes. So here, Jen, let's do the math. So, what happens when we take the charge for tungsten plus the charge for chlorine, and we add them? Tungsten's a +5, chlorine's a -1. That adds to +4, right? And the problem is this is not net neutral. Right? It's not net neutral. We need the total charge of all the positives plus all the negatives to be 0. So what do we have to do to make sure the positives and negatives cancel? Well, our +5 isn't going anywhere. That's just stuck there. So that means we need more -1s, right? Specifically, we need 5 more, right? If we added 5 times the charge on chlorine, this would be equal to +5 -5, which would be 0, which is what we want. So we need not 1 chlorine, but 5 to cancel with tungsten. Let me know if that. Okay. Totally. Good. So also, let's see. Also what 5, let's see. Okay, good. Also, something that's super important to remember is literally you just learned this today, and what time is it? It's almost 6 o'clock. You've literally been doing chemistry for 4.5 hours right now. Just solid, straight. I mean, like the human attention span, the adult attention span is what, like 60 minutes, 90 minutes? So like you have been tackling a lot. You just learned this skill today. And you're doing awesome. You're like actually at a place where you're understanding, even if it takes a little while to get there, you are able to bring yourself to a place where you understand some of the more challenging nomenclature questions I can throw at you. Okay, so let's see. How many? Yes! Okay, Jen, I could not have said it better myself. I could not. Have said it better myself. That was excellent. That is exactly where you need to be. You need to figure out how many more of the smaller ones you need to bring to balance with the two big dudes. So for practice homework in the book, are the answers in the back so we can check once we're done? Carenza, I'm not sure. Dude, and Jen, you are getting it so good. And I mean, it has been a long, exhausting day. Yes, Carenza is 100% correct. And here's the thing, like, this stuff isn't instant clicking kind of material. It's the kind of stuff where it's like you worked on it today. You deserve to let your mind like zen out for a little bit. Hit this thing tomorrow. Come back to it. Do a few more. Do a little bit each day, and it will become second nature to you. Totally. Rome wasn't built in a day, right? And chemistry wasn't taken in a day. We happen to have 8 weeks for that. So, one day at a time, right? Totally. Okay, let me see. I've got the textbook over here. I have a feeling that some of the problems are probably in the back of the book in an appendix. So they have answers to selected exercises. So dude, heck yeah. That sounds like an excellent way to end a long week of chemistry. Okay, yeah. Totally. So it looks like the book has answers to the odd problems. So what I would do is start by doing the odd problems, obviously, and then you can, once you build up your confidence, give the even ones a try. But then you could if you're like certain, because you'll get a feel for it. You'll be like, yeah, I think I got this correct. But if you're unsure of one of the even problems, bring it to office hours, and we can totally do it together, and it'll be good reinforcement that way. So that's what I would recommend. That is the way to go. Teamwork makes the dream work. Alrighty, so it is 6 o'clock, but I don't want to like bounce if you guys still have lingering questions. So are there any last questions out there? See, practice homework are... Yes! Parthana, that is correct. Yep, they're just for funsies. And practice, I guess. Which I've been told makes perfect. Who knows? I don't know if it'll make perfect in chemistry, but it will definitely help you pass. That much I do know. Alrighty, well, in the absence of any questions, I think I'll call this an office hours. Thanks to everyone who came out and who hung out. It's always a blast. You guys are a nice break for me. Oh, dude, you are so welcome, and I hope you have a great weekend too. It's office hours are kind of fun because there's no like I don't have to like prep like with lecture. I've got like lecture notes and I got to make it so far and all this stuff. But like this is just fun and hanging out. Plus, I spend a lot of my time with a 2-year-old, and it's fun getting to hang out here and chat online about chemistry with a bunch of adults. So, thank you all for giving me a good time. And speaking of that 2-year-old, I don't think he's quite in bed yet, so I'm gonna run, say goodnight to him, and I will catch you all on Monday. Keep an eye out. I'll be posting an announcement. Oh, I'm so glad that you find my explanations helpful. Thank you. And Jen, thank you. This is only my second Father's Day, so it's still a relatively new phenomenon for me. Anyways, I will catch you guys all on Monday. You're welcome. You are welcome. Have a good weekend, Carenza. And oh yeah, I'll be like I was like I know there's one last thing I was gonna say. I'll be posting an announcement. It'll have info on the Lab 4 data set for you guys to do some stuff, and a couple updates on a couple other things. Carolyn, you are welcome. You are very welcome. I hope you all have a rad weekend. Alrighty. I will catch you guys on Monday. Later.